Welcome to this section of the course. We'll be approximating areas under the curves with the trapezium rule in this section. So, let me ask you first of all, what's the area of a simple trapezium on the shape on the diagram here? Pause the video and tell me what's the area. What's the formula for this shape? The area of this trapezium is the average sum of the two parallel sides multiplied by the distance between them. I'm gonna call this distance between them because it's not always the case. We're not always going to call that height because in most scenarios, actually in this chapter, we will have our trapeziums other way around. We'll have to rotate them 90 degrees and we'll divide area under the curve into trapeziums that have parallel sides vertically. So let's see. As you can see on the diagram, we can approximate the area under the curve. This is not the exact rule. We're not going to get an exact answer, but the approximation will be helpful when we have functions that are rather very difficult to calculate by hand, or there are not a simple rule to get the answer to. We have to approximate them, and the questions usually tell you whether you need to approximate them or find the exact answer. So, and as we add more and more trapeziums to under the same interval, let's say interval A to B was initially divided into three trapeziums, but if we add more and more trapeziums, we'll have a better approximation because there would be less of an underestimate and less of an overestimate. Okay, so as you can see here, there's a small gap that we are underestimating the area under the curve, underestimating. In some scenarios here, we are overestimating. So these problems will disappear as we add more and more trapeziums interval that we've been given. So let's look at how the formula is driven. I'm going to show you on the next slide. We have just these interval and we are using three trapeziums here. We want to find all three areas in one function. So we can say the area of the first trapezium is this, and the second, in the middle trapezium is where we have y1 and y2 as the height of the trapezium, and y2 and y3 for the rightmost trapezium. If we add these three together, what you notice is that, first of all, let's factorize half h out of every term. Once we've done that, we see that there is two lots of y because this height here is repeated both in the leftmost trapeziums and the middle trapezium. So y1 is repeated there. So we could simplify that to two lots of y1. And again here, y2 is repeated. We'll simplify that to two lots of y2. But the rightmost heights are left as they are. So notice y0 and y3 are as they are, they're not double. So that's because of this. Okay, so when we have when we had three trapeziums, that was the rule. What if we had more trapeziums? Well, the function will always look like this. The the h in our case is not the height of the trapeziums. Height is calculated by f, or by the function itself. Okay, so these y's can be found by evaluating the function itself at particular points. What I'm trying to make you understand is that why is it that only the first and last uh, points x values on the interval. So this y naught comes from evaluating x naught and lower boundary for x and the higher boundary for x, and evaluating the function at xa will give us what y naught is. Evaluating the function at xb, or the very rightmost value for x, will give us what yn is. All the intermediate values can be found and doubled. Okay, so they will be found and doubled by once more evaluating these x values with the function itself. So here really you don't have to change the function, you don't have to integrate the function, you will simply evaluate the value of function at a particular point to find these y's here. Now I've made another video where you can use the table function on Casio FX GC50 to help you calculate these values rather quickly. The distance between these x values is important because that's called the step on the function calculator function. So the step size is what we have here. What you're going to take is the higher value for x, subtract the lower value of x from that, or rather the lower bound for x, and divide it by the number of trapeziums, because that would give you the width of each trapezium here. Okay, so what we are trying to calculate here is the width of each trapezium here. The width is rather mistakenly called h here. I would call it W for width, but the formula booklet it gives you as H, so I'm not going to change that. But be careful that we are actually calculating the width of in each trapezium, and for uniformity, all widths will have to be the same. Now you can use the calculator function where you find it under the table menu, and I believe that's number when you press number 7 on FXGC calculator. So let's see how one example is done. We have a function where square root of 2x plus 3 needs to be estimated by the trapezium rule. The question will usually tell you how many strips to use. So that's the number of trapeziums, that is in this case 4. We've been asked to use upper bound for x to be 2 and lower bound for x to be 0. Okay, so all we have to do is, first of all, we are going to calculate the width of each trapezium, which will be 2 minus 0 divided by 4. Number of strips here is 4, and that's the value of n that we are using in our calculation. Therefore, we have 0.5 for h. Now, let's see what we do next. We make a quick table here. We say that we know that our lower bound for x is 0 and upper bound for x is 2. And we are adding step sizes of half. We have half and 1 and 1.5 in the middle. Those numbers of x that are written in red, we evaluate as they are. And we evaluate all these x values with the table function. All you have to do is type this onto your calculator. The formula is square root of 2x plus 3, and you will get these y values if you evaluated under the right values for x. Now in the video I'll show you how you can change the values of x. If you don't know how to do them, that's fine. Once you got these values from the table, remember these two ends don't need to be doubled, but everything in between these three values need to be doubled. Okay, so that's what we are going to do in our next calculation. 2, 2.3, 2.23, and 2.4 from here, and we are multiplying those three values by 2. But as I said, we are going to leave the very first and the very last terms as they are. This is the width of each trapezium here, and half is because we have half in the formula for trapezium. I showed you that because we have to take average of the two parallel sides. That's it. You put these numbers on your calculator and we should get the correct answer. This is an estimation, not the actual correct answer. Alright, so if you see here, now we are increasing the number of strips to 8 rather than 4, reusing the same function here, so that we will have a better estimation. Therefore, we are going to have to calculate the width of each trapezium again. Number of 8 is the denominator in this expression here, and the width of each trapezium is 0.25. Then we will calculate the table one more time, and we will have more x values and y values. Okay, so the answer for the last estimation should have been 4.44, which was slightly higher than 4.37 in our first estimation. Now, what you see here on the screen is a decimal estimation with trapezium rule. Now, the correct area that we should get should be 3.2, where our function is x multiplied by e to the power of negative half times by x. So n here represents the number of trapeziums, and this number 2.45 is actually way off the correct answer here. But very quickly, as we add more and more trapeziums to our to the estimation under the curve, we will have a better estimation. With 7 trapeziums, the estimation stands at 3.13, and doubling that to 14, we will have 3.18, which rounds up to the correct answer to 2 decimal places. And if we increase that number of trapeziums to 20, we will have 3.195, which to 3 decimal places is a very accurate answer. So happy practicing, and I'll see you in the next video.